Logarithms are the inverse of exponential functions. So exponential growth and exponential decay, we did that. We actually did quite a bit of that in Algebra 2 because exponential problems are very, very real world. So financial problems, all of those things, they're all exponential problems. And we did a lot of it in Algebra 2. Normally when you go into a logarithmic unit like this, you would do a little bit of review, but we're at that place in the year where we have a lot of time, but not very much time. So we have a month of school, but I don't have time to review exponentials and then do more logarithms, or we'll run out of time and then it'll be like, oh, and your finals tomorrow. And so instead, I'm just going to say, hey, I'm pretty sure you have a good hold on exponentials. And if we get to something that you don't remember, we'll kind of review it as we go. But we're going to jump straight into logarithms because there are definitely some things about logarithms that we did not talk about or learn in Algebra 2 that you need to learn, especially those of you who are going on to calculus, whether or not you're taking calculus with me or at college. Okay, so this first part, at the very top, it explains how you read it. Log base b of a, so they wrote it right here. The b is down below, it's a subscript. You would read that as log base b of a. This is an important fact about logarithms, which I'm sure you remember. But log a, which is called the argument, and b, which is the base, both have to be greater than 0. You cannot have a negative argument, and you cannot have a negative base. And then it asks us to study the table of the logarithmic equations below. In each box, write an exponential equation that is related with the given logarithmic equation. They want us to rewrite them as exponentials because they're inverses of each other, just like addition is an inverse of subtraction. Logarithms and exponentials are inverses. So if you remember, the base is the base. So this is log base 3. So now it's going to be base 3. The answer becomes the exponent, and the argument is the answer. I think the easiest thing to remember, if you can remember that the base is the base, the other two numbers swap places. That's the easiest way to remember it. So the base becomes the base, and the other two numbers swap places. So go ahead real quick and fill all those out. Okay, so it says based on the samples, studying the examples, make a conjecture as to how one would find the value of log base b of a. Now, they've already solved all of these. All of these say equal and actually have the answer. But a logarithm is actually an operation. So, kind of like if I were to write down 2 times 3 equals. And then you have to come up with the answer. It just so happens that they did these all already. So really what this question is asking you is, what is a logarithm really asking you to do? So I think the easiest ones to look at and actually come up with the answer are the first line, because we know those pretty well. if you look at this first line, what is a logarithm really asking me to do? Find the exponent. It's exactly what it's asking you to do. It's asking you, what exponent would you put onto the base to get the argument? So, log base b of a again, the ones at the top are easiest to see. But if they had not put this equals 3 on here, and I just had log base 3 of 27 equals, the question is, what exponent do I put on the 3 that would make it 27? I already know 3 squared is 9. 3 to the third is 27, so that's why the answer is 3. This one's asking, what exponent would I put on a 2 to get a result of 16? That's why the answer is 4. Everybody okay on what a logarithm is actually doing? Okay. It gets a little bit more complicated when they're not straightforward, but we're going to talk about that in a second. All right, so down here at the bottom, it says make 3 conjectures about the value of a logarithm based on the numerical relationship. If b equals a, if your base and your argument are the same. So look up at the top and find one where the base and the argument are the same and tell me what happens. It's 1. You might remember that one from Algebra 2. Now, really quick, to show you, if we were doing a big problem, if we were doing a problem like this, we were doing, please excuse my dear Aunt Sally, and we weren't going to do things in our head, we were actually going to go step by step, what would we do first? We would add 4 plus 7, right? 4 plus 7 is 11. Once I do that, what changes from this equation to that equation? It's all one number, and the operation, this, goes away. Because I did the operation. I added them, so the addition sign goes away. Now, we never have a problem with that. But, if I were doing a big long problem and it was log base 5 over 5 minus 6 equals... What did we just say about log base 5 of 5? It is 1, which means the logarithm is gone now because you just performed the operation. You did log 5 of 5. So log is gone. Is everybody with me? Okay. For some reason, once we start putting things in there like log and sine and tan, we have a hard time getting rid of the word and knowing that, hey, you just did the operation, so it's gone now. Getting rid of a plus and minus sign we seem to be okay with, but I'll be honest, sometimes we forget to get rid of parentheses. Sometimes we use them and then we just keep putting them in the problem because, I don't know, because we like them, I guess. But once you've multiplied, you don't need parentheses anymore, do you? Okay. Okay, enough of that. Okay, so the next thing it asks us is actually is if b is less than a, but I feel like the easier one to see is the one below that. If your base is greater than your argument, so let's look at this one. Find some where your base is, and there are several, where your base is greater than your argument. On the second row, there are 2 of them, where the base is bigger than the argument. On the last row, there's 1, at least 1. There's actually several. Is it always though? Because look, on this one, my base is 36 and my argument is 6, and the answer is a fraction. My base is 27, my argument's 9, so it's bigger than my argument and it's a fraction. But look at this one. My base is 5, my argument is 1/125th, so 5 is definitely bigger than the argument. It's not a fraction. It's less than 1. It's less than 1. How to say that, yeah. Alright, so if the base is greater than the argument, the result is going to be less than 1, which leaves, if the base is less than the argument, then the result's going to be greater than 1. And that's the majority of the ones at the top of the page. The base is being greater than arguments. Okay. So now, a logarithm whose base is 10 is called a common log. Now, I'm going to talk to you a little bit about both calculators because it's kind of important. Alright, so I know in this class we mostly use the Inspire. But in some of my other classes, we use the 84. On the 84, it has a common log button, which is right down here by 7, and it just says log. Now, when I hit that button, it pulls up log in the window with the parentheses, no base. Yeah.
You can also set our calculator.
Doesn't matter. Doesn't matter. So if you're not using angles, it doesn't matter what it's in. No, we're not. So when I hit log, it just pulls up the parentheses. There is no base written right here. That is because this is common log. Your calculator has already stored in it a base of 10. Now, on the Inspire, they did away with the common log button because they don't really need it anymore. So if you hit your log button on this calculator, which is down here, it's in blue next to 1 kind of, so you have to hit control. When you put it in, it automatically pulls up a template and there's a place for the base. Now the reason this is important if you're using the Inspire is because textbook writers and test writers, SAT writers, Accuplacer writers, all those, they're still going to write common log with no base. So you have to know that common log is log base 10. Because on the Inspire, you have to put the 10 in. On the old calculator, you don't have to. Now, the old calculator can also pull up this template by Alpha Window 5. But that upgrade to the calculator did not come out until the year 2011. Before 2011, these calculators wouldn't do anything but log base 10 and log base E. So we had to, there's a way to do it. You still have to learn, we're about to talk about it in just a minute, called the change of base property. You still have to know how to do it because we are now advanced enough that some of our logarithms will have x's, in which case these don't help us. We have to understand the operation of what the logarithms are doing. So we'll talk about change of base in just a minute, but I did want you to know the differences between the calculators. And because it talks about common log, and on the Inspire, you have to put the 10. Okay, but just know that the textbook writers are going to write it like this. No 10. So you just have to know common log is log base 10. Real quick, get these decimal answers for me. Just plug them in your calculator. Just make sure we're all getting the right answers and we all know what buttons we're pushing.
Thousands.
3 decimal places. good? Alright, so now down here, before we actually plug these in our calculator and get decimal, we are going to approximate what they might be by using our definition of what a logarithm is doing. So on this first one, remember, we're trying to figure out what exponent can I put on a 3 and get an 81? Is there an exact answer? Is there something I can put on a 3? What exponent can I put on a 3?
Yeah, 4.
3 to the 4th. 3 to the 4th power is 81. So that one has an exact answer. We'll talk about this last column in just a minute. Okay, so what about 2 in order to get 1/8? Now, remember the rule that we just learned. My base is greater than my argument, which means what has to be true about my results? It's going to have to be less than 1. Okay, so now I want you to think about it for just a minute. Could we make a 2 into an 8? With what exponent? Third. 2 to the 3rd would be 8. Well, what if 8's unhappy living upstairs and he would like to move downstairs? Make it a negative exponent. So your answer is actually going to be negative 1. Because 2 to the negative 3rd power would be 1/8. Everybody okay? Alright, log 2 of 9. So I'm looking for an exponent that I can put on 2 and get 9. Is there one? A decimal or a fraction. It's going to come out to be some sort of decimal or something. So what we want to do is approximate. So I know that log 2 of 9 is going to be somewhere between, well, let's see, 2 to the 3rd would be 8, and 2 to the 4th would be 16. So 2 to the 3rd is 8, and 2 to the 4th is 16. So I'm a lot closer to 3 than I am to 4. So approximating, I'm not actually going to write a decimal approximation. We're going to get an exact answer here in just a minute. But if I were decimal approximating this, I would say it's probably going to be in the 3.1 range. Because 8 is almost 9. And so it's going to be a lot closer to the 3 than it is to the 4, right? Okay, so go ahead now and put it in your calculator. And just tell me what the actual decimal answer is. Anybody got it right there? 3.17? Oh, that's close. It said 3.1. It's not 3.1. Okay, so let's do the same thing on the next one. Log 3 of 36. I know that there's nothing that I can put on a 3 and get 36. So what's it going to be between 3 and 4? 3 to the 3rd is 27. 3 to the 4th is 81. So it's going to be a whole lot closer to 3 than it is to 4. So it's probably 3. They got it? 3.26. Right? Let's see. I need to put an exponent on 4 and get 21. It'll be between 2 and 3. 4 squared is 16. 4 to the 3rd is 64. So it should be a lot closer to the 2. 2.2.
Would there be a case where it's like equal distance between like the ranges?
Could be.
So it would matter which I read it.
This is to be 4 and 5. Wait, the 4th is to be 1. 5th is 2. So this one probably is kind of in the middle. What is this one? Anybody got it? 4.24. Okay. Okay, so that whole decimal decimal approximating thing, that's just to give you a general idea of where a number is, but if you don't with your calculator. You don't know how I am about pre-cal, sometimes I take the calculator. And that'll only help you if you need to know whether something is greater than or less than something else. Okay, so now this last column is talking about using the change of base rule. When you do the change of base rule, the whole point in the change of base rule was because our calculator would only do common log before. And so this is what we used before our calculator could alpha window 5 and pull up the actual decimal approximation. However, you need to know change of base rule because when our values become things with x's or polynomials or something like that, then the change of base rule becomes much more valuable to you than your calculator. So, if I was going to do this one, log base 3 of 81, in change of base rule, that would be common log of 81 over common log of 3. If you plug that in your calculator, you should get 4. Now the thing you have to remember about change of base rule is that the base stays on bottom. So this is going to be common log of 1/8 over common log of 2. Put that in your calculator and you should get -3.
So on this one, when you do common log, you plug in 10?
You have to put the 10 in. So this one's going to be, argument always goes on top, the base always goes on bottom, so it's going to be common log of 9 over common log of 2, which should equal the exact same thing. Now, for you guys, especially with the inspires, if you're using the 84, this change of base thing might actually be faster to you than alpha window 5, pressing in the base and the base. It might actually be faster for you just to do log 9 divided by log 2. I probably just hit those buttons as fast or faster than I would alpha window 5 and put stuff in. But on the Inspire, because you have to put the base of 10, it's probably just faster to put in the original logarithm, since you can. But you just have to understand what change of base rule is, and it'll all make sense. If not today, tomorrow. So, log base 3 of 36, as with the change of base property is going to be common log of 36 divided by common log of 3, which is 6. Change of base property. And we did do that in algebra 2. Remember it, but we didn't. Okay, so next on the page. Okay, so this is, I said we weren't going to do like an extensive review of exponentials, and we're not, but we're going to cover this particular exponential quickly because it's important to what comes next. So go ahead in your calculator and put this function into fx. So you're going to go to your graphing page. And then we're just trying to fill out the table. I don't use n, go ahead and use x. And since we're trying to fill out the table, and then I would just control T, remember that gets your table up. Hit menu and hit menu and 2 for table and 5 for edit table settings, and change it from auto to ask so that you can just enter these numbers. plug it into y equals. Second table setting, change it from auto to S. Change your independent value from auto to S. And then go back to the table, and the table should be empty now. Unless you still have some sort. Just the independent. Okay, now I was rounding, but if you actually get down to those values, okay. So if you actually get down to those values, you can see. On my last two, you can see, even though I just put 2.718 on my table, one of them is 2.71814, the next one's 2.71826, the next one after that is 2.718 something something. They're not the same, they look the same on my table. But notice how much my n value, or in this case on our table, our x value, how much it's increasing, and these are only increasing by a tiny little decimal. That's because I am approaching an asymptote. So this says, as n approaches infinity, which is what we were doing with n, we're getting bigger and bigger and bigger, approaching infinity, then my function value is approaching 2.718. This value is called E. It's a script E. It is actually Euler's number. Euler was a Swiss mathematician, and he did lots and lots and lots of things. This is actually called Euler's number. Euler has a constant. There's a Euler and somebody else formula. Euler also came up with some ideas in geometry, and he has some theorems, and he has lots of things because he did lots and lots of things. But this is Euler's number. It is like pi. It is a constant, just like pi, that never changes, but it is irrational. It never repeats, never ends, can't be made into a fraction, and it's on your calculator. On the 84, it's right above the division bar in blue, and on the Inspire, it's down here on the left-hand side when you hit pi, and the template pulls up, E is in there. It's also right here, e to the x is next to 10x by 1. Those are all the E that we're looking for. This constant is very, very related to exponentials. It just kept showing up over and over in all of these problems that Euler and his friends kept trying to work and figure out. This 2.71 business, 2.718, kept coming up over and over and over. So that's why they decided to assign it a special name and put it on your calculator, because it's really important. So it is used to be the base. It's called the natural base, and it is used to be the base of our natural logarithm. We have to use natural log so much that it got a special button on our calculator. It's on this calculator, it's right here, it's ln. And on this calculator, it's in blue, right next to log. It looks like IN on the Inspire, but it's right there, and it's ln also. I don't know why it's natural log and it comes out ln, except that he's Swiss. And so he doesn't speak English. So he doesn't care if it's, most of the time in other languages, where do the descriptors come? A lot of times they come after the words and not before the words. So that's my guess. I really don't know. But either way, that's natural log. It's on your calculator. It is this. Log base e of a will now be written as ln a. No base will show up. It'll just be ln. You have to know that the base is e, because that's going to come in handy a lot. Okay, so now it says, given the expression log base b of a, use the calculator to find the value of log a over b. You can just plug it in, out the window, find the actual decimal approximation. Because I'm going somewhere with this, so just a second. I got 2.727. Now, right here, it tells me to use this expression, log base b of a. So mine was log base 3 of 20. And write it using change of base property. But this time, I don't want to change it to common log. I want to change my base to e. So I'm changing it to natural log. So I'm going to write it as ln 20 over ln 3. And that's what I'm going to put in my calculator. And I got 2.727. Imagine that. Alright, so this one's actually an exact answer. What exponent can you put on 2 to get 1/16? Negative 4. So in my calculator, I got log base 2 of 1/16. So that's going to be natural log of 1/16 over natural log of 2. Should give you negative 4. And it's not approximate, it's exact. Log base 5 of 15. I'm going to change that base. Currently it is log base 5, and I want to change it to log base e. So that'd be natural log of 15 over natural log of 5. Alright, so with this information, what can we conclude about these three things? Log base b of a, common log a over common log b, or natural log of a over natural log of b. What can we say about that? They are all the same. They're all equal. Now, that's going to be important later when we're solving problems, because sometimes it will help us to use common log instead of natural log. Sometimes it will help us to use natural log instead of writing it as one logarithm. So it'll all start to fall into place, hopefully, soon. Alright, so now here they come, the x's. Yay. Alright, so in this case, if the x is in the argument, these are easy. You just rewrite them exponentially. So my base is my base. My answer becomes my exponent, and my argument becomes my answer. Now 9 to the negative 2/3. If this was a calculator portion, you could absolutely plug it into your calculator and get a straight up answer. But what if it's not? We have to remember what this means. Anytime you have a fractional exponent, it is some sort of root. Bottom number in the crack. Top number goes outside. Or you can put it like this, doesn't matter. I'm moving it all downstairs. Why did I do that? Because it was a negative exponent. So he was unhappy upstairs, so I moved him downstairs and rewrote it as a root. Now this case, it's the cube root of 81. Is 81 a perfect cube? Is there anything I can multiply 3 times to get 81? 3 times 3 times 3 is 27, but 4 times 4 times 4 is 64. 5 times 5 times 5 is equal to 25. So there isn't anything. Not to get a perfect answer. So this is it. You can leave it just like that for now. I'm not going to make you rationalize it. Because right now we're working on this. Alright, everybody's sort of kind of okay a little bit. Alright, on the next one I have natural log of x equals 3. So again, if your argument is where your x is, these are easy. You just plug them, you just rewrite them. That's all you have to do. So I have to rewrite this exponentially. So what is my base? E. So this is going to be e to the third equals x. E to the third is going to be a nasty decimal because e is a nasty decimal in itself. I get 20.086. That's right. But if this were the non-calculated portion of the test, you would just leave that as e to the third. And a lot of times in calculus we do leave it as e to the third because that little e, carrying that around is a whole lot easier than carrying around nasty decimals. So that's why we use e and pi, because it makes things nicer. Alright, now, again, my x is in the argument. So this is easy. Just rewrite it exponentially. So I have 3 to the negative third equals 2x plus 1. 3 to the negative third, that would be 1 over 3 to the third, which is 1 over 27. I'm just solving for x now. I'm going to subtract 1 from both sides. I'm giving you negative 26/27. Divide by 2, which is the same thing as multiplying by a half. So you get negative 13/27. Everybody sort of okay a little bit? Kinda. Okay. They're pretty easy if the x is in the argument. Now, on this next one, the x isn't in the argument. Actually, this should be even easier, except they want an exact answer. But x is right here. If this didn't have this radical in it, I could maybe just plug that in my calculator. But that's not going to give me an exact answer. More than likely, that might give me a decimal answer. And I need the exact answer. So let's go ahead and rewrite this exponentially. So this is going to be 25 to the x power equals 5 squared root of 5. Now, in the interest of simplifying this a little bit, I'm going to rewrite that square root of 5 as 5 to the 1/2 power. So let me show you first, and then I'll explain why that's actually so. Okay, so does everybody understand that I went from, obviously this side's the same, that there is no difference between these two things. I mathematically have performed no operations at all. All I did was just rewrite it, because a square root is the same thing as a fractional exponent, so I just rewrote it a different way. Everybody okay? But this way helps me a little bit, because notice where my x is. It's an exponent, and it's up in the air. And now I have a number that is also up in the air. Now if you remember back to Algebra 2, if I can get like bases, I can disregard the bases. 5 times 5 is a base of 5, and that would give me 25. So instead of writing this as 25, I am going to write this as 5 squared. Everybody agrees that's the same thing as 25? But there was already an x up there with it. Now this is 5 to the 1 times 5 to the 1/2. Right? Alright, now I can't disregard the fact that 5 to the 1, what was